So we are on.
Good afternoon to everyone, ladies and gentlemen, and I extend a hearty welcome to Commander Dr. Bhushan Diwan, who has joined us now and who will be the chair for this session. We have had a long day, but very, very fruitful sessions. And there could not be a better way to conclude the day's discussion on this very important topic of materials without talking about smart and future materials. So we have an eminent personality to chair this session. Dr. Bhushan Diwan is a former vice president in Tata Consultancy Services, a senior vice president in Adani Ports, and a pro vice chancellor in noted universities. So over to you, sir. The floor is all yours. Dr. Bhushan, did you hear? Are you online? Looks like he is not online.
He had gone offline. I just reconnected him,
Okay.
and he is on the panel now. Let me check with him.
Yeah, I guess he's online. Commander Dr. Bhushan, please speak up if you can hear me. Yes, sir. Yes, sir. We can see you now. Can you hear me?
Yeah. Now can you hear me?
Yeah. Okay, sir. So
Okay,
I
heard you.
Yeah. Okay. Fine. So the introductions for the chair are over. I welcome all the other distinguished panelists. So the floor is all yours.
Thank you very much, General Srivastav and General Arora. I feel highly privileged to be chairing this session on smart and future materials in this esteemed WebEx. Am I audible? No disturbance?
Yes, yes, Bhushan, go on.
Good, yeah. Basically, smart materials are those that respond to changes in their environment and then undergo a material property change. Now, what are the environmental changes? Things like corrosion, pH changes, water temperature, mechanical forces, and more. And what are the kind of property changes? Property changes like, there are two kinds. There are smart materials, active smart materials, and passive smart materials. The active smart materials are one wherein you can use these property changes to move an actuator, things like artificial muscle, actuator, and passive smart materials where the property changes can be used as using smart material as a sensor. So basically, the material properties, geometric properties, they change under the application of electrical or thermal or magnetic field. And these smart materials have an inherent capacity to transmute energy. Now, what is a smart system then? A combination of active smart materials and passive smart materials. They can sense changes in the environment and then make an optimal response. Optimal response by changing the properties. So, in terms of design, both the sensor and actuator have to be married with appropriate feedback to be able to achieve the function. So basically, how do you program the smartness into the materials? It is basically programmed by the material composition or special processing method or by introduction of defects or by modifying the microstructure so that it can adapt to various levels of stimuli in a controlled fashion. And smart and intelligent are used interchangeably. Now, various types of smart materials, shape memory materials such as alloy, nitinol, alloy of nickel and titanium, which is a corrosion resistance similar to stainless steel, chromoactive materials, magnetorheological materials, electrorheological materials, photoactive materials. Now, let's take an example. how this is already, some of the smart meters have been used and developed. Basically, in the smart meters have been developed to suppress vibrations and change shape in helicopter rotor blades. Shape memory alloy devices are also being developed that are capable of achieving accelerated breakup of vortex waves of submarines. And similarly, different adaptive control surfaces are developed for airplane wings. And the research is on to focus on new control technologies, that smart materials and design methods for placement of sensors and actuators. Now, I want to highlight three things here from my perspective. I think for us in India, one is to think of taking a stock of whatever is happening in the world. On the other hand, if you go to the very basics, things from bottom up, I think my sense is that basis for future original research for us in this area comes from bionics or biomimetics, meaning studying how nature deals with its problems and using those for our purposes, like Velcro. Velcro has come from those flowers, which have hooks in the end. There are so many other things which nature does very beautifully, and that can be a great source, because we're all research and development professionals here, to think in terms of, unless we're able to do independent, basic research in the area, and then applying that, point is we'll be just copying others, and then we will not have that competitive advantage. Second very important point is, these smart materials, they have a particular problem. They can't be done by used and applied by, routine machining approach. So basically, the concept of DFM, design for manufacturing. In a sense, when you design, you have to see that, is it manufacturable? If it is not, then, we are in trouble. So practical application is design for manufacturing. And also one step going forward, so this is a big area for us, that if design for manufacturing is seen, correspondingly, the machine tool building, the machine tool design also needs to innovate in light of machining new smarter materials. And the last point I want to make and close here is that basically there is a problem that when we talk about, all of us are defense, DRDO, people may point fingers at us. Well, it's so much money down the drain. Defense means so much money down the drain. It's a cost center. Sorry, it is not. Fortunately, smart materials indeed are truly a dual technology. Like drones are, well, drones are a different kettle of fish. It is not smart materials. Like smart materials can be very much used in health monitoring, building automation, wherever making life comfortable in a big way, where whatever is dull, dirty, and dangerous, in most of the applications you will find the smart meters can come into picture. So with this, I will now call for the presenters and so that they can give you a presentation. So can I call for the first presenter, Dr. Raja?
Yes, sir.
Okay. I have so a hearty welcome to all the colleagues on the panel. So I think the first presenter we have is Dr. M. Manival Raja, F and Group Head of the Advanced Magnetic Group in DMRL. So, sir, the floor is yours to cover your topic.
Okay. Can I start, sir?
Please.
Is it visible, sir, my slides?
Yes.
Okay, sir. Good afternoon to everyone. So today, first of all, I would like to thank the organizers for giving me this opportunity. Today I'm going to talk on smart materials for futuristic defense applications. Smart materials are subset of functional materials. So DMRL is working on functional materials for many years. So the latest development in this area is that the development of rare earth permanent magnets technology, which is being transferred to IREL, Indian Rare Earth Limited, which is a part of DA.
Dr. Manuel Raja, please press F5 and make it full screen.
Okay, sir. Okay, sir. Full screen. Now it's okay, sir.
Yeah, better.
Okay. So DMRL, as I was telling, DMRL is working on functional material. This is the recent development in this area is that the technology transfer for production of this rare earth magnets for defense and other strategic applications. And the production plant is being constructed and being established at Vizag by Indian Rare Earth Limited. Development. In fact, this technology was developed a long time back, and there is now the requirement for the large scale production. So hence, its plant is being set up at the Vizag. So after establishing and developing this technology for the rare earth permanent magnets, now the current focus is on smart materials for futuristic applications. The classification of smart materials, basically smart materials can be a metal or alloy, or it can be insulating ceramics or polymers. It can be any kind of materials, but based on that function, it can be classified based on the driving force. So the well-known the smart material is piezoelectric material. For example, lead, bismuth, the lead, barium, francium, titanate, lead-based material, oxides, those are oxide materials. Those are well-known material that is used in many actuator systems. Then magnetostrictive material, that is another smart material. Here, the driving force is magnetic field, and this magnetostrictive material is used for again sensors and actuators. Then shape memory alloys. So when you're coming to shape memory alloys, there are two type of shape memory alloy. One is thermal shape memory, which is driven by the thermal energy. The other one is magnetic shape memory. Magnetic shape memory, that is the driving force is magnetic field. Then thermomagnetic materials, thermoelectric materials, magnetocaloric materials, and the photosensitive material. These are the various types of smart material. So as I was telling, though there are different type of smart materials are available, there are three main the driving forces, three driving the classes. The heat, the thermal energy is the major, the one, the important driving force. Then the electrical field and magnetic field. These three type of smart materials are very famous, and these materials have been extensively already used in the many applications. So when you say heat, so here the thermal energy is going to be a driving force. The example for that kind of shape memory, as a smart material is shape memory alloy. It's basically the nickel titanium. So here basically nickel titanium, it changes the shape when you change the temperature. So you can activate the actuate. You can do the desired functions by simply changing the temperature. The other type is the electric field driven smart material. Here basically when you apply electric field to the particular material, it changes the shape or it produces a strain. So vice versa, these are irreversible effect. So similarly, if you apply stress on the material, it produces an electric field. So the typical phenomena is the piezoelectric material or piezoelectric. The very typical example is lead zirconium. The lead zirconium titanium, lead zirconium by TZ is one of the very famous material. So when you say smart material, the first material coming to as an example is lead zirconium titanate. Then the magnetic field. The magnetic field is also can be used as a driving force. So based on that, the materials can act as a smart material. Is magnetostriction, then magnetostrictive material. That is magnetostriction. So that is basically a magnetic alloy. So it's commercially available. That's terminal D, and in fact, even DMRL we are developing this different kind of material. Then another very new smart magnetic shape memory. So as I was telling, there are two types of shape memory. One is thermal shape memory, that is nickel titanium, whereas the magnetic shape memory is again nickel-based alloys, nickel, manganese, gallium. This is there is no temperatures involved here. By applying a magnetic field, you can change the shape. Like so, the driving force is magnetic field instead of the temperature. So this is the kind of activities going on at DMRL. So we have taken the R&D activities and R&D projects on these smart materials. The first one is the magnetostrictive material. This activity was taken for the development of a sonar device for the NPY. Like so, here this magnetostrictive material will be replaced by the piezoelectric material. The current technology is using the piezoelectric the transducer in the sonar, but the sonar using piezoelectric material works at very high frequencies. So in order to reduce the frequency of operation, that's the idea is to use the magnetostrictive material, which can be used at the very low frequencies, about 1 to 2 kilohertz. So by reducing the frequency, we can increase the range. So that is the advantage of magnetostrictive smart material. The second activity material system which we are working on is the magnetic shape memory alloys, which can be this is very similar to the nickel titanium, but here the external stimuli which is going to drive the system is the magnetic field. Again, these materials can be used as sensors and actuators in many applications. Then third material system that DMR is working is on, it's a very new material system, magnetocaloric materials. These materials, this is another class of smart material. These materials are very useful for the magnetic refrigeration, which is an emerging technology coming up. And the last one is we are also working on the piezoelectric material, which right now we are concentrating the piezoelectric material for the electronic filter devices for the seekers. So I will start with the magnetostrictive material. The phenomenon of dimensional changes in a substance when it's exposed to the magnetic field is called magnetostrictive material, magnetostriction. It is also known as Joule effect because it was discovered by Joule. So it was named as a Joule effect. The magnetostriction can be positive or negative. It can be positive or negative depending upon the changes in the dimension of the material. So, for example, when there is no field is applied, this is the original length of the magnetostrictive rod. When you apply a magnetic field, there is an increase in length. So now the lambda is positive. So this is a positive magnetostrictive material. So when you apply, when the material is exposed to the magnetic field, it changes, its dimension is increasing. So now what we can do, now you apply a time varying magnetic field to this kind of material, then this the rod starts to vibrate. So these vibrations leads to the production of the sound waves. So when you apply a time varying magnetic field to this rod, it produces the sound waves which can be used as a transducer in the sonar systems. So these are the not only sonar, this magnetostrictive material have many applications. So the sonar is one of the defense applications. It can be used as actuators. It can used in the smart wings for the actuations, the adjusting the wing positions, and the another important application. Another important application is it can be used as a vibration control systems. Then it's used in fuel injectors, speakers, ultrasonic cleaner, like that. So many instruments. There's another important application: high force linear motor. It is used in the aero systems in many places. Then adaptive. It can be used in the micro pumps and mine detections, hearing aids, so seismic sources, and it's also used in the surgical tools. So these are the various applications using the magnetostrictive material. So DMRL is working on this material for the last 5 to 6 years, and we have developed the manufacturing technology for making these rods. So this is the typical rods for the magnetostrictive material, which is basically the dysprosium, terbium, iron. This is the material system that we have developed at DMRL. And so basically this is developed by the directional solidification technique, which facility has been established at DMRL, and we have made this the process technology for making the magnetostrictive rods. These are the final product that has been developed at DMRL. Typically this is the 20 mm, 30 mm diameter of the rod and 100 mm length. These rods will be used in the sonar as a transducers. So these rods will be subjected to the time varying magnetic field, and when it undergoes a time varying magnetic field, it produces the sound waves, which is used in the sonar systems. And this is the typical characterization curve of the material. So basically it's a magnetostriction is measured as a function of magnetic field. You can see that a maximum strain of 1400 have been obtained in DMRL alloys. The next one is the magnetic shape memory alloy. This is very similar to the nickel titanium, but as I said, the actuation is the phenomenon is due to the magnetic field. When you apply a magnetic field, the magnetic orientation of magnetic domain in the material, it changes. As a result, it changes its structure. So that is the principle of this shape memory alloys. This is also having a lot of applications like magnetostrictive material. So here, this is one of the example how this magnetic shape memory alloy can be used in the actuator. This is one typical example. This is the linear motor which is developed by the one Adaptov Finland company using the magnetic shape memory alloys. So DMRL just started this material. This material is also having similar applications like magnetostrictive material. It can be used for sonar, actuators, and sensors. So DMRL, again, we are using the same processing technique which is used for magnetostrictive material for this material also, and using directness solidification techniques. The material system that we have developed at DMRL is again nickel-based alloys. It's a nickel, manganese, and gallium. It's a ternary alloys. It's a ternary alloy systems, and you can see here the difference between the magnetostrictive and the shape memory alloy is there is a structural change in the magnetostrictive material, the shape memory alloy, which gives rise to the change in dimensions. This is the typical the crystallographic structure of this material. This is the magnetic properties. So the next material is so the magnetic refrigeration system. So this is based on the magnetocaloric material. This is one of the emerging technology. So in the magnetic refrigeration, so the magnetocaloric materials used as a refrigerant. In the conventional refrigeration, the CFC, chlorofluorocarbon, is used as a gas compressor. So used in the gas compressor, the compressor is the main part in the conventional refrigerating system. Whereas in the magnetic refrigeration, there is no compressor used. Here, a solid state magnetic material is used, which is, for example, this is the rotating disc, which is made of magnetocaloric material. when this disk is rotating in presence of magnetic field, when the material goes inside the magnetic field, it's heated up, and if it comes out, then it's cooled down. By continuously rotating this magnetocaloric material in and out of the magnetic field, then it can produce the cooling effect. So the advantage of this technique is that there is no compressor and chlorofluorocarbon is used in this technology. And this is a solid state, instead of CFC gas, a solid state magnetic material is used as a refrigeration system, the refrigerant. And since there is no CFC is used, it is eco-friendly. It's eco-friendly, and there's no the dangerous to the ozone layer. And since there is no compressor is used in this technology, it's a very compact and the efficiency is very high. The maximum efficiency can reach 60 to 70%, whereas in the conventional refrigerator or air conditioning, it is works only in 30 to 40% efficiency. So in terms of efficiency and performance, in all these ways, this magnetic refrigeration appears to be very promising, and many countries are working in this technology to realize this technology for the practical applications. So one of the most important requirement for realizing this technology is that the magnetocaloric material. The magnetocaloric material is the heart of the system. So when this magnetocaloric material is exposed to the magnetic field, it is heated up. That heat is removed by circulating the water. And again, you remove the magnetic field, it comes down to the disordered state. Then it takes the heat from the surrounding. As a result, it gives the cooling effect. So that is the principle of the magnetocaloric material. So the material which should have the large change in the entropy when you apply a magnetic field. So that is the figure of merit for this class of material. And so DMRL is working on this material technology. This material is basically on rare earth alloys again, gadolinium, silicon, germanium alloys. And this is the composition of this alloy. These alloys were developed by the vacuum arc melting techniques. These are the alloy cut pieces you can see. It was melted by the vacuum arc melting techniques. And these materials being operated near the transition temperature so that the maximum change in entropy is observed. And you can see this is the various stages of the development, like chemical analysis and the magnetic thermomagnetic measurements and the structural studies. All these characterizations will be carried out to understand the material system and produce a material with the required properties and compositions. This is the functional properties of this material. You can see the magnetic entropy is measured as a function of temperature. The maximum value of 22 joules per kilogram Kelvin have been achieved in the alloy which is developed at DMRL, which is much higher than the reported in the literature compared to other alloys. We are getting a higher value because of the different the process techniques used for making this material. So we have developed this smart material for magnetic refrigeration applications. Now we are interacting with GE, the global engineers in GE Bangalore for designing and making a magnetic refrigeration system. So that interaction is going on. We are also identifying the Indian industry, which is interested in using this material for making magnetic refrigeration for futuristic applications. So this refrigeration system can be used for various defense applications also. So that is I have covered only mainly the smart material magnetic smart materials. We are also working on nickel titanium based the thermal shape memory alloys. Then we are also working on piezoelectric material like lead zirconium titanate and the non-lead compound piezoelectric material like the barium, calcium, zirconium, the titanate. So those materials are is being investigated and developed at DMRL. So finally, I will come to the conclusion that I have covered three important smart materials. All three are basically the smart based on the magnetic smart material. So one is the giant magnetostrictive material, which is developed for sonar applications, which will be used by NPOL, DRDO lab. And another material is magnetic shape umbrellas, which is still under the R&D because there's still some issues are there in the using in the applications. The R&D is going on. And the magnetocaloric material, which is for the magnetic refrigeration system, the refrigeration can be used for many defense applications, as well as it is having a lot of potential in the civilian applications. So as far as this alloy system is concerned, the material have been developed. We are looking at partners for taking up this material for making a magnetic refrigeration. With that, I will conclude my talk. Thank you.
Thank you very much, Dr. Raja.
Thank you, sir.
It's a delight to know that, you are trying to take this technology to real life. First
Yes,
of all,
sir.
you mentioned the example of, helping out Indian rare earths for their plant in Visakhapatnam. Then you also talked about trying to reach out to General Electric. I think, as they say, proof of the pudding is in eating. And if that is where the proof of concept will come and proof of our research will come. And
Yes,
what is the timeline for really, if I may ask, in trying to bridge the hold hands with GE? What is the timeline, target line?
With respect to the GE interaction, we have some problems. So GE is asking 100% IPR rights. So Cupro is not willing to give 100% IPR rights for the GE.
Right.
So the DRDO policy is that the 50-50, like GE 50% and DRDO 50%.
Okay.
That is not agreeing. So that is where some issues are there.
Okay.
So now almost we have stopped the interactions because without the IPR agreement, we are not able to forward further. And right now we are looking at an Indian partner who can take up this material for magnetic refrigeration.
Right. And another minor question with respect to the, other countries, let's say China, for example. How are
Yes,
we
sir.
placed vis-a-vis in terms of cutting edge technology? Are we there? Are we behind? How behind or how forward?
As far as this magnetic refrigeration is concerned, all the countries are R&D level only. So no practical refrigerator has been come to the market.
Okay.
Still in the R&D level, like it will take some more time. Like, but it's one of the very important technologies which is required for India.
Bhushan sir, all these applications are most advanced alloys and they are called almost like compounds. And process windows of them is extremely difficult. So the processing technologies are very, very specific for certain applications. So the shapes of the components, materials required, all minute details, engineering has to be done. So large number of parts have to be made whenever it becomes specific to the system. So when we have a system, we have the capability of making them. So that is what is demonstrated by DMRL in a large extent. And we can take up whenever there is a large number at an industrial level or with a foreign collaboration or within India. So we have the capability. That's what DRDO shows. We have the technological capability to do all these advanced materials, even of the latest of the world.
Okay. Thank you so much. So let me now introduce the next speaker, next presenter, Dr. N. Iswara Prasad, Scientist H and Director, MSRD. He has made significant and outstanding contributions to the design and development and airworthiness certified production of several aerospace and other advanced materials, especially for the LCA.
Bhushan sir, I'm already introduced in the morning in the session 2. I'm only continuing my talk.
Yeah, I know, but there may be new audience, I presume.
Please. Okay,
so
sir.
Okay, just last few words. Indian Space Program, missile programs, modular composites, LCH armor, and radar absorbing stealth materials. So with that, over to you, sir.
It's an honor and privilege for me to talk in front of such an audience which are keenly listening to me to look at what Indian defense requirements in terms of materials and what is that we can achieve today. And then compared to the first part where I introduced, Sudhanshu, you can fix the presentation. compared to the first part what I presented, only to show that what all India had worked on from the beginning till an exportable items. So we had talked about what is required for aero materials because that was a aero session. Now I'll switch over, next slide. A few products, again aero products only are concentrated, but you can see that some more products I'll talk about them in my presentation on DMSRD. You will see that a lab like even DMSRD is a small lab. What all we do for Indian defense and what we can do for the nation. So when I complete this 15-minute presentation, you will see that the materials canvas is very large and one has to be selective. Next slide. One has to be selective to suit a particular material for a particular system. This also I presented. I talked about the only engine India has developed and qualified and put into production is the Kaveri's jet fuel starter, where in which the casting components, 4 of them have been done, and that is one by the technological innovation, which even requires talk about getting a uniform grain structure in the rim and the blades. So these are all some of the innovations which are done to make them qualified. Otherwise, these aero components will never get qualified. Next slide. So this is a complicated technology. I talked in the morning that Supercast 247A remelt stock. That means it is already melted and remelted. Only by that we can get a compositional control. But still it is an extremely difficult technology because we are looking at a very highly sensitive chemistry without which we cannot get this gamma prime distributions done at a microscopical level. You can imagine each of the precipitate is only a few nanometers to a few hundred nanometers. And all of them have to come into the grade where you can go right from directionally solidified blade to these are all, each one is a one grain. And in that grain, we should have all this phase distribution of particular manner. And then we also have to have some serpentine type of air channels. Only then we can have the aero blade, which will be qualified. So the qualifying of this melt itself will be proven at the blade level, not at the melt level. So that kind of aero qualification comes into picture, and the development which is done in the lab will have to be taken to the industry in the limited series production, then in a mass scale production, then assembly, then the engine testing, which is a long way off. Next one. Then we have APL castings, very much required for the multimode radars, which are mounted on the LCA to do all telecommunications, which are required for each of the aircraft. And these things you can imagine, right from 1 millimeter to 32 millimeter wall thickness had to be done in a single casting, and the casting is an air melt casting. And an alloy is a simple aluminum alloy, but the casting itself has to be done in an air melt. And when we, as I said in the morning, when we made this alloy to be qualified a grade 1, grade A qualification, the yield was 0. That means all castings were falling below the standard because some minute inclusions and things like that will come into that. And then radiologically, when we qualify, none of them will qualify because the stringent aeronautical qualification preludes us not to use that alloy. But when we change the standard from A to B, allowing certain amount of only few what you call ppm or even a fraction of a 1 weight %, we could able to go up to 20% qualification or yield. Then the later it has become when I left as a Semilac, we could able to go up to 65% castings were through, which is an international record in terms of air melting castings. So if there is enough requirement, continuous activity, then constant development, it's called concurrent development, then we can achieve anything. This is the only thing what we require is a system which is required in a long term. And the gestation period in any materials development is very high. So one has to have patience to handhold with the developers and the industry to mature materials and systems for the ultimate use in an aircraft or a tank or even a stealth aircraft, not what you're talking about, or even a small subsystem like bulletproof jackets and things. I'll come to that and you will realize the importance. The story is the same, but the contents will be different. Next one. Then we have a very critical half alloy. These are titanium 6 and 4, 6 aluminum and 4 vanadium is a workhorse alloy for titanium, because that is an alpha beta titanium alloy which gives the best of the strength and fracture toughness as well as fatigue properties. But there are special alloys where formability is important, and these tubes will have to have very high impulse loading. That means if you are putting some gas or some fuel in this or fuel mixture, all of that will be experience very high frequency fatigue cycle, and such 2 lakh number of cycles, the minimum has to be stand by entire of this tubing. If you cut open the aircraft, you can see lot of tubing on the aircraft, and this tubing is done only by 4 or 5 sizes of this titanium half alloy tubes, and very critical to do that. And this is being done in a multifaceted development program. Now we are shifted from 4 imported sources to 2 imported sources. Then there was a almost the immediate requirement of doing indigenization because there only one source left from the foreign. Then now we have in a capability to even export because this complete technology is mastered, and then we can do the tubing for LCA 2 or LCA 1A on a production basis. Next one. Then we have this beta titanium alloys, which are considered the technology. If you can do this, is supposed to be an advanced country in terms of material processing for aeronautical applications, because beta titanium is extremely difficult to make. In fact, many people fail during the process of ingot making itself because it will crack into 2 if you do not even cast it, let alone process it to the final shapes. So we could able to get the thin sections like this from the beta titanium alloys, qualified now aeronautically, and then this is the only beta titanium alloy which can replace maraging steel 1-to-1 in terms of specific strength and still retain the much more advantages in terms of specific modulus as well as the little higher thickness sections, which is not possible for a high strength alloy like maraging steel. But it has got extremely good corrosion and erosion resistance. That is an added advantage. So landing gears which are made earlier from the maraging steel are replaced with beta titanium, and the LCA2 will have landing gears from this alloy. Next one. Then we have light armors developed by DMSRD. As I said, it requires what is a single parameter called aerial density. You can change the material composition, modular structures, the composites, and then they are extremely important when weight of the structure for any particular system is important. But though it is aeronautical, light combat helicopter is not as critical as a personal body armor. Let me tell you, the bulletproof jacket requires an aerial density of equal thickness around 22 to 27, according to the latest Indian standard. Whereas the equivalent one for LCH is only 30 plus or even 28 plus. So what we are seeing is even an aeronautical grade material is inferior when we come to the soldiers' comfort or its what you call security or safety. So that is what it becomes. So the level 2 armor of the helicopter is met by the lab, and then we have the technology to transfer to the Indian industry. It is a question of who takes this technology and makes it a viable economical solution for LCH, so that LCH will have one vital component of up armoring when it becomes an exportable item. Already it is an exportable item. It should become much more exportable, even the countries which will give it with a light armor. Next one. Then we have this carbon-carbon brake discs, which are extremely important for any Indian program to be sustained, because the carbon brake discs are always imported, and the technology India has developed is a very, very vital technology, and we have to further move on and develop, because these are all not only required for military aircraft, but very much required for the civilian aircraft. Until the civilian aircraft brake pads are made, we cannot match the international cost in terms of the brake pad technology. Let me tell you why we select carbon. Carbon as a element is the only one which retains its frictional properties even at very high temperatures. Most of the metals are even oxides and carbides. They become what you call sticky when the temperature rises very near to its melting point, or even 0.7 to 0.8 times homologous temperature. That is the melting point expressed in terms of degrees Kelvin. So the carbon is the one which retains its frictional properties even beyond 0.8 TM. So the carbon-carbon composites are developed and they are qualified. The only thing is from 350 LCA landings, we have to go to 800. Then we are internationally best. And limited trials of our own Indian effort would show that we could go up to 500. But consistently, we have to reach 650 plus. Then only we'll become international player if it had to export this one. But for Indian program, this is acceptable. Next one. Then I stopped here in the morning talking about the Indian prototype for select aerosystems. I cannot cover all the prototype development that is going on for various Indian aerosystems, but I'll give a few examples which will tell us what are the challenges we face, how we overcame, and how we delivered. Next slide. This is the first one I'd like to tell is a big success recently. The Astra air-to-air missile is the one which will make our Sukhoi world competent and lethal in terms of air penetrability or air attacks. So the aluminum alloy, which is only 2014, had to be scooped out from the machine parts. But now we have a near net shape technology and other things which can make it much more productionized. And qualifying this aluminum alloy itself is a big challenge, because without a smooth release from the aircraft, the aluminum itself from the compared to the earlier steel and other missile release mechanisms and the missile itself, it will become very, very difficult if you don't do a correct alloy and correct what you call aeronautical procedure. And this missile comes under the aero grade because it is launched from an aircraft, a fighter aircraft like Sukhoi, and later it will be tried and tested from our own LCA. Then our LCA will become what you call a system on itself, where it will become, when it becomes weaponized, its value will go 10 times higher. Next one. We have Helena missiles, which are also very, very important. In fact, the NAV, which was very difficult to produce under the IGM-DP program, which was launched by Dr. Kalam sir, is now matured for helicopter. So the Helena mounted NAV missile is called Helena. And this is an extremely difficult missile because it has to take only aim of only very short distance, and the telemetry has to be done very carefully. And lightness of that is very critical. So we were trying to take titanium alloy, which has got this nominal composition, and the properties are 820 yield strength, and it has a very little fracture toughness, 40. Let us compare this 40 value. I'll not talk about the complicated number like fracture toughness. The Marazin steel has got 100, 120. Okay, so it need to have, for the Helena to qualify, a minimum fracture toughness of 55 plus. So when we did a alloy design, what all we could do is just reduce the interstitials which are there in the titanium alloy, Ti644 alloy, in terms of carbon, hydrogen, oxygen, and nitrogen. We reduce its total content from 0.45 weight percent to less than 0.1% weight percent. This is called extra low grade because the low interstitials will actually decrease the yield strength, but they tremendously improve the fracture toughness. But by heat treatment of this titanium alloy, even at the low interstitial, we could almost retain the yield strength and improve the fracture toughness by 50%. That's the biggest achievement. To evaluate that one, we had to generate a special fracture mechanics methodology based on J integral. So when we did that one, so 25 is the absolute number, 32 is what is achieved number. That means 25 would have given 52 to 55, and 32 is the achieved number, which gives 62 MPa root meter when we convert this. This has been only the qualification mark for the Helena missile material, which is made from the titanium 6-4 with an extra low interstitial contents. Such an efforts are required whenever there's a particular system gets hampered or even stopped, even in the ground trials, and we will not able to move to the further trials. So this kind of things will always hamper our progress, but we'll have to overcome all this to move forward and then deliver in the ultimate system. Now Helena will be placed order for the LCH and other things, and then we'll have a super lethal light combat aircraft. Next one. Then we have a very important guided missile, the Garuda and Garutma. Garutma is actually guided. Now it is made even, Garutma is made stealthy. I'll talk about it. And the very important one, because this is where very low cost effective weapon will become available to Indian Air Force and other agencies where we can use. And imagine it has got lots of materials in that built in. So it is not one or two critical materials. There are many materials which have to be TIE certified and productionized at economic cost to make even 20, 30, 40,000 AASBs. So these are the large, huge numbers are required. So economy also comes into picture as compared to the high value missiles like Helena or Astra. Next one. Then I am talking about very briefly the program which we led from DMSRD and 5 other DRDO laboratories as a DMSRD as a nodal lab to only make the stealth materials on a reproducible manner at the industrial level and then produce them at different centers, Defence Lab Jodhpur, Naval Material Research Lab at Ambernath, Advanced System Lab at Hyderabad, Aeronautical Development Establishment at Bangalore, then R&D engineers at Pune. All these people with the interaction with the ADA. Dr. Subbareddy talked in the morning, what all are required for this kind of a system for the Tejas. Now we are moving to AMCA, which is actually weight-wise more because the stealth comes with a penalty. We have to have not more than 5 to 10% extra weight, 5% actually, extra weight to incorporate the stealth features so that we can retain the lethality and become invisible to the enemy radars so that we can have an AMCA system. It is not that stealth aircrafts are not made, are not tested, are not tried in the world. For the last 60, 65 years, different countries are trying the stealth aircraft, but they are not because the radar capabilities are also improving much faster than stealth air capabilities. Now the Air Force Chief wants us to do 1 to 100 gigahertz multiple solution for the stealth capability. Almost impossible to do it in the 5% or 10% weight addition, but we'll have to attempt. So now we are at a stage to give 2 to 14 or 16 gigahertz. When this program is defined, we have to give 1 to 18 gigahertz or 2 to 18 gigahertz. So 16 to 18 gigahertz, only the 2 gigahertz region is extremely difficult to reach in terms of the stealth RCS reduction. So the 4 prototype components have been identified, which will make our AMCA world best, and then we should be able to do this. And the materials under present condition. Morning somebody asked, what is the kind of production levels and what is the kind of testing we'll do and how the qualification happens. In the production level, we have only a demonstration projects where we demonstrate the technology or the system, in which case we'll make maximum 3 prototypes or 3 into 2 prototypes. Whenever a prototype fails or a component fails, we'll have to make the double the number and prove 100% redundancy or 100% qualification. Once that is done, then a mass number is produced in the intermediate level where 10 in 100 or 20 in 100, depending upon the user specification, we'll have to test. That is going subjected to statistical analysis. Then we'll talk about an aircraft. Ultimately, the aircraft has to prove 1 in a million failure, then only it will become not military aircraft, of course, but the civilian application. But the military aircrafts are also asked to do at a very high reproducibility. That is, the material property reproducibility, and the quality. Once we do that, then only the material or the material-based components or the subsystems can get integrated into the main system or tested at the main system level. AMCA pilot will not sit down in the cockpit until we prove all this at the ground level and limited takeoffs and landings. Next one. So a bit of more details. The air intake duct, several configurations are possible, and these many material systems are already developed. They are under testing. Not only electromagnetic testing, we have to do mechanical testing, because these are all the ones which are non-metallic materials, and they have limited mechanical properties as compared to the metallic materials. And temperature wise, the composite, the polymer based composites are nowhere compared to metals or in ceramics, but they have the advantage of lightness. So the composites which are made based on the polymers and polymer matrix composites added with what you call some radar absorbing materials, they'll become viable one. If you see, all these things are very, very complicated systems, and all of them are being matured now. And not only EM and mechanical, we need to even look at the environmental properties, because once the systems are developed, because the polymers they wither, they have to have a bench life, which is 5, 10, 15, 20 years. So all these things need to have very rigorous environmental properties. All of them have to be proven in a program. Then we have material ready for AMCA, which should be going into the first prototype by 2024. And by 2022, we have to make the first prototype of each individual prototypes. Then it will be integrated and tested as a system. Then we have, yeah, next.
Dr. Prasad, sorry to interrupt. But
yeah, I'm completing in 2 minutes, sir.
Yeah, okay. Okay.
Next one. So these are all the important material programs that the DRDO had worked, where I'm a part of it. So you can imagine, as many as in the programs that I know of national importance, 22 programs are aeronautical materials programs compared to 40 which are equally important and tough for other systems. So, but what is the advantage? Aeronautical materials, if you develop, they can easily be adaptable to other systems and other what do you call applications. So that is the biggest advantage. And today morning, the chairman DRDO talked about national material policy, in which I am the chairman for the stealth materials committee and also a member of the aluminum materials and ceramic materials. Then we had held the Niti Aayog programs for the technical textiles. Similarly, there are national material standards committee under MOD. All these things only make a material that are available to the Air Force or even air systems. Next one. Then this is a program where aluminum alloys are developed in a composite program by DMRL. And now all aluminum alloys as a value addition are available for all these systems. Next one. Then we have a new alloy called aluminum lithium alloy. Whole world is looking for this alloy, but until new aircrafts are made and the new design is accepted, these materials will not take shape, because shifting from one material to another material will invariably increase the cost of the system, but 5 to 10%. When we do that, and we have to get the cost compensation in additional features, and lithium is one of the best alloying element to add aluminum to reduce its density, but it has got its own problems, and now we realize what are the limitations and work within that limitations to make this alloy. If at all AMCA is made with aluminum lithium, it will have property advantages, but cost will be high. 5 to 10% cost will be high. Next one. Then we have a steel bank. I am talking about the other application. For example, Indian missiles, we had put a Maraging steel bank of almost 300 crore rupees worth. A few thousand tons were put in a bank where we can make various shapes of the missiles so that the missiles can be made in less downtime. Next one. Then we have silicon carbide, a wonder material. If at all a future engine will be made only from ceramics, all ceramic material, it will be made from silicon carbide. Not as a monolithic material, but as a fiber reinforced composite. And we are trying to do the precursors from this lab to a fiber, and fiber to a component, whether it is a vein or a disc, things like that is a huge technology gap. It is only a 15, 20 years down the line, we can expect all ceramic engine. And Vijay Pitle had given a talk, and then what is the future for this kind of an activity. Next one. So next one. So what I wanted to tell you is the aircraft are defense materials, are cutting edge materials, and they are the latest and the best. When you do the development technology, manufacturing technologies, establish the infrastructure, rest everything can be built very easily and very automatically. And the number multiplication is very, very easy as long as a country like ours, like India, we say that we will meet our requirements from our own capabilities. That is the only thing required, will to do our own self. Atmanirbhar Bharat, Jai Hind, and God bless India. Thank you.
Yeah. Thank you very much, Dr. Prasad. You've given a very excellent exposition of the kind of futuristic work being done under your leadership. You covered the missile applications of the futuristic materials, smart materials. Also covered the stealth material. Since a couple of quick questions from you, very short questions. You know, Dr. Prasad, any collaboration is possible, or has it been investigated with labs like, you know, CSIR's lab, DMR lab in Bhopal? That is my first quick question. Second is transfer of technology from your lab to a private company like Bharat Forge or Tata, you know, who are trying to make use materials and alloys for manufacturing missiles. Thank you.
So I'll answer the first question first. That is interdepartmental interactions, and CSIR labs are the ones meant for quick industrialization and do the industrialization projects, so that the technologies developed, advanced technologies like defense technologies are translated to an Indian industry. We have active collaborations with CGCRA, for example, DMSRD itself. Similarly, each of the defense lab, the 558 labs, we have very strong ties and then collaborative programs with other labs, not only CSIR, but other departments as well. But let me tell you, sir, there is a immediate requirement to talk about taking it as a system, as a complete solution. Okay, sir. And in that case, evaluation has to be done by a high-level committee, and whosoever gives it is for the country. Okay, sir.
Yeah.
And the second one, what you had asked is, are we transferring enough to the industry? Now, DRDO has come with a policy of technology transfer. 1,000 technologies are transferred to Indian industry. My own lab, we had given 12 critical technologies to 41 Indian industries in the last 1.5 years, including the bulletproof jacket given to 7 industries today, and then 2 more industries are asking for it. We are holding it because giving the technology for too many people without too many orders is also not correct. Thank you, sir.
Thank you. So I think, General Srivastava, we don't have any other speaker, or do we have?
So we don't have now any more speakers for this session.
So let me summarize this. And I think, for example, it is well known that going forward, smart materials are going to play a big role in aerospace technology. I mean, it's well known that, for example, self-repairing is one very good example of smart materials, you know, wherein you embed some thin tubes within the surface, within the material containing uncured resin. And, you know, when the damage occurs, these tubes break, exposing the resin which fills any damage and sets. So self-repair could be very important in inaccessible environments such as underwater or in space. I think this reminds us of a spider or a lizard. When lizard tails break, after a few days, it has grown another tail. Another very good example of a smart material could be used for, you know, non-destructive testing and health monitoring of engines and parts, and thereby making MRO very economical. MRO as in maintenance, repair, and overhaul, very economical and efficient, so that in a battle situation, we maximize operational availability of the platform assets. But as Dr. Prasad also pointed out, rightly pointed out, I think the crux of the main challenge is using smart materials. The critical challenge to my mind is that the material per se in a lab could be invented or designed or whatever, created. The crux of the matter is it machinable? I mean, the material is utility is only linked, is so useful, or only as much useful as much it is machinable. So if it is not machinable, it is of no use to us. It's a theoretical construct. So it may be such a machinability may be amenable only for 3D and other modern manufacturing technologies. So perhaps I'm certain that part of the material development, this kind of testing, using it, looking at machinability aspect may also be looked at. So should we throw the floor open for questions now?
We may ask if there are any questions.
Any questions from the delegates? Maybe we can spend 5 to 7 minutes to answer any.
There are two questions. One is, are there any projects involving rare earth materials which we are undertaking for the army? And second is, can you comment on the status of chemical industry in the country to support large-scale production of these materials with sufficient raw material supply?
Very nice. So I think both these questions pertain to rare earths only, right? So we should perhaps ask Dr. Raja.
The rare earth one, maybe Dr. Manivel will answer.
Yeah.
The second question I will answer, sir.
So can we first make it open to Dr. Raja to answer the first question? Dr. Raja, are you there? Dr. Manivel Raja, are you there?
No, he's not here.
Oh.
He's not
So
here.
maybe Dr.
Then,
Prasad.
Ravi sir, let me answer. So because I know the answer, so let me do that.
Sure.
So
Pleasure.
the rare earths are the ones which are available in plenty because Indian ilmenite or the titanium source and the beach sands are the sources of rare earths, and then DMRL and BARC, and also some of the private research institutions have done the rare earth extraction technologies which are very, very essential. For example, all the advanced permanent magnets, they require rare earth metals. But the import costs are very, very low because China dominates. So we have to have a policy where the pricing and the sourcing will have to be worked out, and we have to produce these metals at an economical scale. Then only it is possible to do a rare earth technology, and also rare earths are required at a value addition level. We can always should depend only on Indian sources. These are my suggestions, and there are committees which are done for the rare earths, and we have now an ambitious program to even own mines for the technologies and sites for the rare earths from the abroad, so that we can do the rare earth extraction economically from the other sources as well. So these are all some of the things which Indian government as well as DRDO as well as other agencies are thinking, which will become immediately reliable. Another 3-4 years itself, the rare earths required in the country will become available. The second one is the chemical industry. Indian chemical industry is very vast and strong, but they work on low value products mostly. So it requires at least some percentage of their profit, if not the investments, should be invested in advanced polymers and polymer technologies, which we are importing because the volumes are low. This is another paper which people are writing, so that the Indian industry should invest on advanced materials, especially the 3 materials which are identified are the polyethylene, polyurethane, and similar kind of those things. Then we have the glass and the epoxy composites. Then we have very important ones like thermoplastic polymers, which are extremely difficult to make, but that only will be able to give us high temperature capability. So there is always papers done in the various agencies which are pending. But Indian chemical industry, the raw material development is severely lacked for low volume requirements. This is my humble submission to the Indian industry that they should do definitely invest. If not their investments, at least the profits should be plowed back to the advanced materials. Thank you, sir.
But Doctor, in this domain, is any DRDO lab working? Because see, being an infrastructure kind of thing, you don't expect private players to come in.
Sir, we have got recently 40 crores project only to do 2 precursor development. So DRDO does its might and best, but other people have to become a national effort, sir.
There was another question somebody flashed it about nitrogen something. I couldn't read it properly. What was that?
He talked about large-scale production of chemical industry, the facilities as well as the technologies for large-scale production of the raw materials and things. It's related to the same, sir.
Okay, fine. Another small query, Dr. Prasad. In
Sir.
terms of TOT to private industry, you have said you have given it to so many, so many industries.
Sir.
They include MSMEs also, by the way, like
Yes,
bulletproof jacket.
There is no differentiation of a particular, but we have a procedure which is already laid down as a 200-page document by the DI2TM, which talks about how transparently we are doing the TOTs. Okay, sir?
Right. About this transfer of technology only, do you monitor the person, the industry which has taken the technology from you? I mean, they have to come back to you with a prototype, right?
So
Only
the
then
TOT is given for 5 years, and within the 5 years, we handhold with the industry and absorb the technology at their site, and then help them in the productionization. And any new developments come within that, we automatically transfer them as an upgradation. But after 5 years, they have to apply for a revision of the TOT, sir.
5 years is rather long, isn't it?
5 years, but many products will become obsolete in 5 years, sir, because the systems what we are.
Yeah. Okay. I think.
Okay, sir. I mean, maybe I'm wrong in stating 5 years, maybe it is 10 years. But I remember that the TOTs we are given, even 2001 is revised now, sir. So it is not that you are right. Some of them require long gestation periods.
Okay, I think with this we can, because we've had discussion also, and we have summarized the two presentations also. So with this, maybe I think we could treat it as closing remarks over. So may I now hand over the forum back to General Srivastav or General Arora? Thank you.
Thank you so much, sir. I think the chair has conducted a very, very informative session. Your initial opening remarks itself, they sparked a lot of inquisitiveness and interest in the way smart materials can be tweaked. And thereafter, it came out quite clearly as to how a lot of efforts are being made by the DRDO. And throughout these sessions during the course of the day, without wanting to repeat much of what has been said, what comes out quite clearly is that disruption in supply chains will remain. This geopolitical, geoeconomic uncertainty is not going away. So therefore, Atmanirbharta, particularly in materials, is the start point. Manufacturing, of course, is a close allied second. So therefore, whatever policy measures have now been undertaken through DAP 2020 and DPEPP 2020, etc., they are just a start point. What needs to be done, much needs to be done by the users themselves. RFIs, before the users initiate, they have to check whether the material is available indigenously or not. And then we have to insist through our joint ventures and offset obligations that OEMs need to source the material from here and transfer technology. These actions have to be translated on ground. Like there are provisions now that suo moto, the industry can approach for certification. Even if, let's say, the product is ready, there's no demand, but they can, to save time tomorrow, they can insist on suo moto certification. Likewise, they can offer a product suo moto, whether or not an RFP for that has been initiated. So these are the things like certification, quality assurance is a big loss of time and cost. So therefore, all those things which were mentioned as to how modeling needs to be done. Two speakers, industry speakers, we are speakers from Siemens, they brought it out very clearly what needs to be done. So there are a lot of takeaways from today's webinar, And it remains for me to convey our heartfelt thanks as Director CENJOWS to all the chairs, and to begin with Dr. Satish Reddy in the morning, as also all the eminent panelists for having shared their very, very insightful observations. At the end of the day, we will put together the essence of the webinar, and IMR and CENJOWS put together will concise it into implementable policy kind of recommendations from our side of what could be done by the ministry and by the headquarter IDS. So that's the basic aim. Thank you so much.
Sunil sir, my offer of publishing what is publishable in the open domain for the Indian industry is still open to you. Please use that platform of Metal News of Indian Institute of Metals. We'll publish that, and there is no page limit, sir.
Oh, thank you so much. We definitely remember that. I'll put it on record that you are a partner with us for that. We're on the same page. As also a recommendation made by Dr. Vinayak that we need to hold another session on the semiconductors. Very pertinent observation. We will take that forward. So with that, I conclude, and I thank CEO IMR, General Ravi Arora, for making this whole webinar possible. I also thank all the members of CENJOWS, particularly Group Captain GD Sharma, who have worked towards making the event possible. Thank you so much, all of you, sir. Best wishes. Over to you, General Arora, sir.
Thank you, sir. Thank you. On behalf of the Center for Joint Warfare Studies and Indian Military Review, it is my privilege first to thank Admiral Jain, the CISC and Headquarters Integrated Defense Staff for having supported this event. Also to thank Chairman DRDO and Secretary Defense R&D, Dr. Satish Reddy, for having graced this event with an inaugural address, and for having provided a number of speakers from the DRDO. I would also like to thank the Army, Navy and Air Force Headquarters and DGAQA and Midhani for having nominated able speakers. Our lead sponsors, Dassault Systems India and Siemens Industry Solutions India, and the sponsors ANSYS for having supported this event. To all the chairmen of various sessions, Air Marshal Wagle, Dr. Seema Vinayak, General Sanjay Verma, and Commander Dr. Bhushan Diwan. To Ernst & Young for being the knowledge partner and having prepared a paper on this subject, which will be sent by email to all the participants. And to all the delegates for whom basically this event was organized, for having sat through the whole day. Hopefully next year we will have this event again. It will become an annual feature. This was the first time that CENJOWS and IMR took up this subject for the webinar. A video of all the sessions will be available later on YouTube after editing. And tomorrow, today's session, recording of today's session will be rebroadcast to same timings for all those who have missed it or want to go through it again. Some of the questions remained unanswered, and these are going to be sent to the concerned speakers for direct interaction if they like. And as the director pointed out, our recommendations will be made to send to headquarters IDS. And last but not the least, big thanks to team CENJOWS and to my team at IMR who worked during the last 1 month to make this event possible. Thank you, sir. Bye-bye.
Thank you so much. All the best.
Thank you very much, Ravi sir.